Okay, thanks, Mary. Do you see my slides?
Excellent.
Okay, so what I wanted to do today is just share some experiences that I've accrued over the last seemingly 20 plus years in the context of, let's say, living and breathing open source projects in the, in geodynamics specifically. So it's, solid earth geophysics, but most of the things I'll talk about today relate to experiences I've had to geodynamics, but I think these experiences, translate and transfer to they're common to many disciplines in earth sciences and outside of earth sciences. So I wanted to tell you a little bit about myself and where I came from, and sort of not exactly why I'm here, but why I do the things I do. So my sort of introduction to open source software started in 2001, where I did an internship at a supercomputing center, so the Victorian Partnership for Advanced Computing. And this actually was an internship I did before my PhD actually started. And during that internship, I was basically told or given some advice that open source is the only way for advancement. I worked on used a particular open source package, Portable Extensible Toolkit for Scientific Computing, or PETSC. And I, used this tool over the next year and ended up, as it turned out, using it for the next 20 years and becoming a developer of it. But, what got me started, what I learned from my first experiences of using this software package was great software is a team effort. It's not a hero code, right? It's not written by one person. It's a team. It could be a small team, but a cohesive team. Using products and software that other people have written can be a huge time saving. You don't have to reinvent the wheel and re-implement everything. I actually learned an awful lot by just studying well-designed open source software. The fact that it was open meant I could study the source, and I learned probably more about linear algebra and software engineering than I did taking undergraduate classes. So studying well-designed software was something I walked away with an appreciation for. I also learned that there's nothing perfect, right? There's no perfect software. But when you use the right tools and you have a good team, ambitious software endeavors or enterprises that you may want to commence are actually tractable. So having witnessed the benefits of this open source world and experiencing things firsthand, I definitely concluded that this is the way. And, great engineering accomplishments, it's common knowledge that they're achieved by teams of individuals or groups of teams, be it, designing and building an SR-71 Blackbird or a Hadron Collider. And actually, software is no different. We have lots of examples, right? You have the Linux kernel, GNU compiler tools, Python, Julia, Firefox, Blender. These are all projects that are open source, driven by communities and individuals that devote their time, their free time, to work on these projects and make them great. And I probably bet that everyone in the audience has some familiarity with at least one of these open source tools. So, we're familiar with great software that's free. We appreciate they come from team efforts. So I kind of embraced that and took it on board and made it more or less my mantra. And that started and continued through my PhD and through my postdoc and through the rest of my academic career. So when I started my PhD, we basically had a task to develop a completely new open source geodynamics package called Underworld. This was work done at Monash University, headed by Louis Moresi, who's the sort of mastermind behind the whole project. It's very ambitious. We were going to start from scratch, develop something that's fully, massively parallel, scalable, using modern design techniques, modern software, exploiting open source packages. And our product that we would like to produce was also going to be open source. And nothing like this existed back in 2001. 2005, the computational infrastructure for geodynamics was formed, CIG, and we would interact with them. And this is, the sort of the beginning of an open source geodynamics world, right? There's now a group, an organization in the US that promotes this and advocates it and enables it. And we started to work with those people quite extensively. And I still work with CIG, actually. And so I took that experience as a PhD student and continued to, push it, basically. I moved to Europe, continued to do open source software in the context of geophysics. But, I encountered plenty of resistance in the last 10 years to doing this. And I wanted to give you some of the quotes that real people have told me, well-respected scientists, and then try to disentangle what was maybe their concerns and what some of the realities are to sort of set the scene of like what's myth and what's reality in the context of these statements. So my code is rubbish. I'm embarrassed to have anyone to look at it. I don't want or have the time to support a horde of new people, new users. I spent my PhD getting this stuff to work. I cannot just give it away. I don't want to get scooped. Now, these may all sound like pretty reasonable things, but I can tell you the people that have said these to me, actually, most of them have changed their mind. Sometimes it took a decade, but they have kind of come around to the point of some people fully embrace it. And now their projects are open source, even though they said that would never happen. Some people at least have started to use version control and even accept pull requests and so forth from other users. So there's hope for everyone, even when you're fossilized. So my code is rubbish. I'm embarrassed to have anyone look at it. Where does that come from? Maybe a fear of criticism, maybe fear of losing respect from your peers when they see how bad you write code. Maybe you're just lacking a little confidence in the results. But the thing is, the realities are, these are my sort of learned realities from doing this and experiencing it over a long period of time are shown in blue. And the things that I want to, or that I have seen, and my experiences have been that, code can only be improved with help, with input from others. Code is critiqued, not the developer. You're actually praised for giving things away. You're not criticized as a developer. So this is sort of an emotional response. I'm embarrassed to have anyone look at it. But if you think rationally and you really care about the quality, reliability, robustness of your code, then you will embrace help. And it's free. You're not having to write grants to get it. People are willing to volunteer their time to it. The other thing to remember is people want to use your code. They want to invest in it, right? They believe actually in it. So they're motivated and enthusiastic to make it as good as possible. Blocking them out is really counterproductive towards everyone's common goal, which is doing better science. So, let them in, let them help. I don't want or have time to support users. So people are basically scared of opening up a Pandora's box and getting a million emails that ask for help. And the answer is, well, and you may just not want to deal with that. That's fine. But let's think rationally. If you make your software publicly available, you put a license in there, there's nothing that says you're actually guaranteeing or promise support to anyone that downloads your software. Okay, so you still have the right to ignore emails, and I think everyone's pretty good at doing that. So it's not a contractual agreement once you make it open source that you're actually going to help people. However, you have to think about this in another way. Every person that's a potential user of your code is actually a potential collaborator, science paper co-author, a developer or maintainer or tester, or the person that potentially wants to answer those help emails, just waiting to blossom, right? So if you don't allow them to come in and help them, you're maybe not helping yourself actually either. So supporting and training users, motivated, enthusiastic users of your software is an investment in your software's future, okay? And it actually alleviates you of a lot of the burden of doing everything yourself. It's shared across the users, okay? So something to bear in mind. I spent my PhD getting this stuff to work. I'm certainly not giving it away for free. So what could this mean? Where could this come from? Some sort of emotional tie to the software, maybe PhD trauma, lots of cursing and hours spent banging on the keyboard trying to make things work. Maybe it's a fear of losing control of the PhD time investment, the work that you invested. Maybe you just believe that your code is too complex for others to use, understand, or maintain. And so what I think are the realities, though, are that the percentage effort that someone spent in their PhD getting something to work doesn't necessarily reflect complexity of the software, but possibly it's more indicative of the time spent in the self-education phase in terms of that you had to go through yourself in regards to algorithmic development, software engineering, language specifics, applied math. Most of those people on those intro sides are self-taught. I know Marin, myself, and Elisa all self-taught computer programmers. So, when you do this work on yourself in your PhD, you spend a lot of time making all the mistakes and then trying to figure them out. So percentage effort, it's not really reflective of complexity. More eyes, I put eyes in quotes because I really mean brains and fingers on the keyboard, looking at a code, make it better, right? It makes it simpler, more efficient, more transparent, and easier to maintain by more than one person, which again goes back to longevity and sustainability of your software and unburdening yourself from having to be responsible for every piece of every character, every line of in your code base. So more users equals more maintainabilities, goes towards longevity and sustainability. And a developer's available percentage effort decreases over the course of their academic career. As a PhD, you have 100% of your time to just work on your code. Then you become a postdoc, then you'll become a mentor, then you'll have faculty and department meetings to sit on. And the amount of time that you have to actually write code probably goes down to 5 minutes a day or 0. I see everybody. I see Marina and Elise nodding their heads. So, you know, in the interest of keeping your software alive, it's advantageous to unload some of that work onto other people that are willing to help you, right? Users, maintainers, developers. You can't do everything all by yourself for your entire career. It's not tractable. I don't want to get scooped. Okay, this is legitimate. Possibly it's happened before, maybe in a non-software context. It's emotional, but possibly not a particularly rational response to giving your code away in the form of an open source product. The reasons are one click, ready to go science papers are just available out of the box, just not there, right? That doesn't exist. You won't pull something and then generate a science paper in 5 minutes, right? It's not going to happen. And that's even true when people have taken the effort to enable reproducibility. It doesn't work that easily. And you know your code as a developer better than anyone else. So it seems really improbable that somebody else is going to know how to use your software more effectively than you to produce great science results. Doesn't seem like it's possible. And in 20 years, I've never ever seen this happen or even heard of it happening. In fact, my experience is you're much more likely to get scooped showing unpublished work at an AGU poster, not by giving open source software away. So, so what do I conclude from all this? Code doesn't have feelings or egos, individual developers do, right? So going on from that, that would probably explain why people just have pushed back a little bit on some of these topics over the years, right? These are generally more emotional responses rather than pragmatic or forward-thinking responses. Okay, now I wanted to switch a little bit and go back to this Underworld Gale example that I mentioned earlier, which was software developed for studying geodynamic processes. And essentially, Underworld kind of stemmed from Monash developments, CIG built on top of it, created something new called Gale. And because there was a user base of long-term tectonic modeling in the US, sort of connected with CIG, a community started to grow. That's this blue ball that I've drawn here. Okay, so you can think of it as CIG is making software, developing software, giving it to the community. It's sort of one-way street. So there are things that the community can do to feed back into that, to contribute back, right? You can make code contributions, you can fix bugs, put efficiency improvements, feature enhancements, enable new features, okay? So this is a sort of feeding back into the development bubble to enhance or advance the field. And the other thing you can do is to share models, okay? So this could be input files, pre and post processing scripts, special patches to enable special functionality for models, documentation on how to conduct either the forward models or do the analysis. And after working in open source fields for a while, it dawned on me that actually, yeah, code contributions are one thing, but actually giving models back to the community is a much more powerful way to advance and forward the field because the software already existed. So it's like second level advancement of the field is, share models. So sharing models is great. It reduces spin-up time of new projects, enables reproducibility results, overall lifts the kind of standards of open source modeling in the geodynamics community of how you should use open source software in a fair and transparent way. And it encourages openness and community building and collaborations by giving your things back. Okay, so I wanted to show you something that we did. We did this in 2012. We basically set out using some open source software. We wanted to basically lay down a kind of very detailed, thorough set of instructions that were going to go into a supplementary material of this G-cube paper on how to reproduce our results. We weren't aiming for bitwise reproducibility. We'd just be able to like someone to make the same figures, essentially, that we created using Gale simulations. So these are numerical forward models of metamorphic core complex development. So what we had is a supplementary material, and it contained instructions to obtain, configure, and compile all the external dependencies, instructions to obtain the sort of what I call the geodynamic software stack, which was 7 independent mercurial repositories. Each repository had a specific commit hash that we wanted people to pull and build with. We had to patch 4 of the source files. So we included patches and instructions on how to apply the patches, and we provided, our input files that we used to generate the simulations we showed, and we provided all the post-processing scripts, MATLAB scripts that we used to generate the model-specific outputs. So we were pretty pleased. We thought it was a good, thorough coverage of all the possible things that could go wrong. And so as a sort of fun test for myself, I decided to try and reproduce it in 2023, so on the weekend. And I should put a little footnote there that actually Gale is not maintained or developed by CIG anymore. It's hosted, it's there, you can access it, but they don't invest any manpower into it. The community went into a different way. But just because it's not maintained doesn't mean these results that are in that paper shouldn't be reproducible. The software still exists. It's still out there on the internet. You can still access it. So, it seems fair game to try and put ourselves to a little test and see whether we did a good job. So the first thing we can see, actually, or I realize, is if you go and look at the supplement of this paper, there's a very nice README file, plain text ASCII thing. You can read it, explains all these things you should do. And it refers to file names that you don't find in the supplementary material, because G-Cubed in 2012 decided to rename all our files. And the only thing we could do to identify them is, call them a script or an input or a patch. Unfortunately, even those labels were messed up in the auto-generated text file names that are here. So it's very difficult to even follow the steps, because the README refers to mcc1.xml, but actually the file's called that thing. Doesn't even have the right extension. So you have to do a lot of legwork to just try and figure out what it is we're asking you to do. So let's suppose you can deal with that, get past it. Things have improved. I'm not, criticizing G-Cube. That's just how it was done in 2012. They didn't ask for this. We wanted to promote it because we thought it was great, but it didn't really work with their policies. So the next thing is that I noticed on the weekend is that all of the mercurial repositories were migrated to Git, which is a good thing. But unfortunately, all the commit hashes that were in mercurial are not preserved when you migrate from mercurial to Git. And also, all the 7 repositories were merged into a single repository. So basically, all our detailed instructions that said HG clone, this commit, this URL, the commit hash is not valid and the URL is not valid anymore. So that's a bit of a mess. And the 7 repos are one, so you don't really know how to get all the specifics, the specific commits from the 7 repositories in one place and built. So the source is a bit of a mess. And the patches can't be applied because of that. So, the improvements and enhancements that CIG did, again, this is not a criticism, it's just what happened, right? CIG wanted to move from mercurial to Git, which I totally endorse. They did that, but in the process caused some unexpected problems downstream 10 years later or 6 years later. So I failed. I couldn't reproduce my own results, even though we tried really, really hard in 2012 to document what we did. I can't reproduce them. So, long-term reproducibility is actually hard. Despite your best efforts, it's difficult. Now, things are a bit better, or a lot better actually in 2023. For one, you have dedicated platforms like Zenodo, so data hosting alleviates some of the issues. It doesn't automatically solve the software stack issue though, right? That software still has to be available. Commit hashes if you need them, they should still be valid. So if you put everything into Zenodo, maybe you would be okay, but everything would mean the software you used plus all of its dependencies, which may be 35 packages. That's not really scalable. So compiling a 10-year-old code, a complex piece of code with a very complicated software dependency tree on modern hardware is actually always potentially challenging. Pretty sure none of this stuff that if I could have downloaded it, I'm sure it wouldn't have built on an ARM architecture, for example. So that's an issue. It's always been a problem. Containerization here would really help, right? And it would be an appropriate solution for this situation. We have a very complicated software stack. Open source code developments generally promote code reuse. So actually the number of dependencies in software is not going to reduce in time. It's actually going to increase. So in the sort of interest of thinking forward about how to, enable long-term reproducibility of your scientific results, this issue of dependencies, maybe through containerization, needs to be sorted out. So short summary before I finish up is, yeah, open source is good. There are lots of examples of where it works, examples that we're familiar with and use every day. The benefits outweigh any inconvenience, in my opinion. The sort of next frontier in my mind, or in my opinion, going beyond open source science or open source software, is to be able to have that reproducibility built in as part of your sort of publication model. Is to, if you use those tools, you should be able to reproduce results, and the community should be able to reproduce results from open source software. It's still challenging, but it's a worthwhile endeavor. It'd really be great if journals just helped a little bit in doing this, right? Some do, but it'd be nice if more of them did. I had some incentives to encourage or facilitate and enable the reproducibility. For example, maybe offering more option than just plain old Zenodo. So over on the right is my sort of dream of what I would like to be able to do in my GQ paper, is instead of having a button in the supplement that says launch in Binder and spin up a notebook, I'd like to be able to launch it in Docker, for example, that I get all the source, all the software dependencies, and I can just run my model there in the container. And it's all part of the journal, and I don't have to store it or manage it or maintain it. That's my dream. It doesn't exist. Maybe next decade we can see if we got there. Okay, that's all I have. Thank you for listening.
Thank you so much. That was really a nice, beautiful journey to watch. And I was nodding a lot about the rubbish code. This was great. No, it's interesting. And part of the day we'll continue in thinking about containerization. And in the educational context, I'm following the same model that you're seeing here. When you teach a class on the software, and I want to be transparent with all the dependencies and reproduce everything, and then dependency failed and failed and failed, and I spend my time instead of preparing lecture dealing with this thing. But if you containerize everything, it actually is still within that container. Everything is in there, but it's just a lot easier. I'm optimistic we'll get there before the next decade, maybe.
I hope so.
Hopefully. Maybe Alice can speak on Seismica's behalf for that, maybe one day.
Yeah, it's actually a good point, but it takes some time to move the community as a whole. Like we will cover containers this afternoon on day one for a reason. But that would be really an interesting approach to take. But our authors have to be educated how to set it up.
That's what I mean by journals could help, right? There could be some incentives and some process to enable and facilitate these things and incentivize the whole process so people are actually more inclined to do it. So, one of the things I didn't have in quotes is like, what are people's reactions to data policies in AGU journals? I didn't put those there, but most people a lot of people that I encountered think that that's just, a burden, and then they basically want to figure out the least useful, least annoying path to satisfy the journal without actually really thinking about why it's there, because there's no real incentive in their mind to do it. So you can't put these things in and expect people to make containers for papers without giving them something back or incentivizing, or at least explaining why it's useful. It has to be sort of something else, something for Seismica to think about.
So it's human adventure, huh? We code with absolute terms, and then we have to account for the human impact and factor. Well, thank you so much, Dave. That was fantastic, and I'm glad you pioneered a lot of that in the early 2000s, because we're still learning how to do it today. So thank you so much. That was wonderful. So now we're going to have a little break. I'm going to get coffee. However, we're going to set up a couple of breakout rooms. I have not done that many times. And so I'm going to put 7 breakout rooms, and please join it